This brings me to introduce the next speaker, Jyoti Yadav from Technobis Crystallization Systems. So she will discuss how to unlock the power of solvent selection, and I'm sure she will have good use cases for some of the collaborative model. Thank you very much.
Thank you, Masivia, for the introduction. Good morning, everyone. I am Jyoti, application specialist from Technobis Crystallization Systems. And today in this session of translation to industry, I would like to focus on selection of solvent and talk about unlocking the power of solvent selection, solubility, nucleation, and role of AI in crystallization. So during the presentation, first, I will give a brief introduction about Technobis and the collaboration between CMAC. Then I will share a case study to see the effect of solvent and solvent system on solubility, nucleation rate, and crystal habit, in which I will first share the experimental procedure or methodology followed to determine the solubility, nucleation rate, and cooling crystallization experiments using Technobis instruments. And then I will share the results to see the effect of solvent system on solubility, nucleation rate, crystal habit. And from crystal habit, we will see the role of AI to predict crystal shape, size, and particle size distribution. And in the end, we will look into the future collaboration with the CMAC to look into the lab for future, that is automation. Technobis Crystallization Systems provide instrument for accelerating crystallization research. The product line of Technobis consists of 3 multi-reactor crystallizers with application at different stages of solid-state research and development. First is Crystal Breeder for early stage discovery with unique features of different crystallization modes like cooling, evaporation, vapor diffusion. It has 32 reactors with working volume of 0.1 ml. Then Crystal 16 is for the solubility and solvent screening. It has 16 reactors with 1 ml of working volume. And the latest version of Crystal 16 has integrated software for automatic nucleation rate analysis. Then crystalline is for the optimization of process, where you can vary different operating parameters like different crystallization mode, cooling, evaporation, anti-solvent, seeding. Then different types of stirrers can be varied and then optimized. Crystalline, along with measuring the temperature and transmissivity, it captures the real-time images, and because of that, it has unique application in crystal habit control, particle size distribution, process optimization, formulation, and crystal growth rate analysis. And for the polymorphic transformation, it can be attached to Raman spectrometer. This is during the installation of the crystalline instrument last year, and the collaboration facilitates the development of cutting-edge technology and to build instruments that align with industry demands. So coming to the case study of ascorbic acid, commonly known as vitamin C, is an essential compound with a wide range of application in pharmaceutical, food, health, and personal care industries. So solution crystallization is an important step for the separation and purification of ascorbic acid. Now, water is used as a solvent for crystallization, but there are other solvents also that can be used for crystallization, like alcohols. And from where the question arises, which solvent to select, or in general, why solvent selection is important. Because the solvent employed for crystallization controls the thermodynamic parameters like solubility, supersaturation, solid-solvent interactions, then kinetic parameters like nucleation and growth rate kinetics, and final crystal attributes. The solvent employed for crystallization will control the crystal size, crystal habit, and polymorph. Therefore, this case study focuses on the effect of solvent and solvent composition on crystallization of ascorbic acid. Coming to experiments, first to see the effect of solvent and solvent composition, 4 pure solvents, water, and 3 alcohols, methanol, ethanol, and isopropanol were selected, and then binary solvent systems were prepared by adding alcohols to water, 3 binary solvent systems of water methanol, water ethanol, and water isopropanol used using this equation below. And these are the concentration. These are the concentration in mole fraction, and to determine the solubility, 4 concentrations of ascorbic acid were added in 1 ml of solvent system, and the solubility was determined using crystal 16 instrument by polythermal method. So the instrument measures the change in the transmissivity with the change in the temperature, which determines the clear and the cloud point. Clear point is defined as the temperature upon heating, where first 100% transmissivity is obtained, which indicates the complete dissolution of the solute. Then cloud point is defined as the temperature upon cooling where last 100% transmissivity is obtained, which indicates the appearance of the crystals. Then using clear and cloud point, one can determine the solubility curve and metastable zone width. I can use a, yes. So yeah, and the difference between these two, clear and cloud point, is known as metastable zone width. And these are the various operating parameters used: heating and cooling rate of 0.3 degrees Celsius per minute, temperature range between -10 degrees Celsius to 80 degrees Celsius, depending upon the boiling point and freezing point of the solvent, then stirring speed of 600 RPM, and the solvent volume for 1 ml for each binary solvent systems. Then for the calculation of nucleation rate, experiments were performed to determine the induction time using crystal 16 instrument. To determine the nucleation rate or induction time first, 4 different samples were prepared at different supersaturations, and it is calculated using this equation, where Ci is the amount of ascorbic acid added and Cs is the solubility at temperature where we want to keep our solution constants. For example, here we keep our solution constant at 20 degrees Celsius, so Cs is the solubility at 20 degrees Celsius. So the solution were first heated to high temperature so that everything is dissolved, and then they were crash cooled at a very fast cooling rate of 20 degrees Celsius per minute and kept at the same temperature for long duration. Then at the time at which the transmissivity decreases, it indicates the appearance of the crystals represented by this cloud point. And these steps were repeated more than 80 times for each supersaturations. Then further, the instrument calculates the nucleation rate using classical nucleation theory. According to classical nucleation theory, the nucleation rate J depends upon the supersaturation ratio S according to this equation, where A is the kinetic parameter, which represents the number of active sites available for nucleation, and B is the thermodynamic parameter, which represents the activation energy required for nucleation to happen. Then these are the number of experiments performed for the nucleation rate analysis, and the solvent system considered were water, then binary solvent system of water ethanol with increasing concentration of ethanol 0.2, 0.4, and 0.6 in mole fraction, and similarly water isopropanol solvent system, binary solvent system of water, increasing concentration of isopropanol 0.2, 0.4, and 0.6. And these are the supersaturation considered for each solvent system and corresponding concentration and number of induction time or data points collected for each solvent systems. Then coming to cooling crystallization experiments, the cooling crystallization experiments were performed using crystalline instruments. First, a known amount of ascorbic acid was added in 3 ml of solvent systems and first heated to some high temperature till everything was dissolved. Then it was slowly cooling at a cooling rate of 0.5 degrees Celsius per minute to 20 degrees Celsius and kept for some time. And during the whole process, the images were taken at an interval of 2 seconds. Then coming to results, these are the results for the solubility experiments performed using crystal 16 instrument. And from this curve, you can see that solubility increases with increase in the temperature. And this is the solubility of ascorbic acid in pure solvents in comparison with the literature data. And from here, we can see that ascorbic acid has high solubility in water and it decreases in methanol, ethanol, and isopropanol. The reason for decrease in solubility is that ascorbic acid is a polar molecule, therefore it has high solubility in high polar solvents like water, and its solubility decreases with decreasing polarity in methanol, ethanol, and isopropanol. And from these graphs, at any fixed temperature here, we can see that the ascorbic acid has high solubility in water, and it decreases with increasing concentration of alcohol for all 3 water methanol, water ethanol, and water isopropanol solvent systems. And again, it can be attributed to the fact that adding alcohol reduces the polarity to an intermediate value depending upon the concentration of the binary solvent systems, and hence it decreases the solubility of ascorbic acid. These are the probability plots generated by the crystal 16 instrument or software, and each in different solvent systems, and each curve represents one supersaturation, and each point represents one induction time data point. And from these graphs, the instruments calculates the nucleation rate J and growth time Tj by curve fitting the experimental values. if you want to see the effect of different solvent systems on the nucleation rate, this is comparison at 1 supersaturation. And here we can see that nucleation rate decreases with increase in the alcohol concentration for both water ethanol and water isopropanol solvent systems. And on the other hand, the growth time increases with increase in the alcohol concentration, which indicates that ascorbic acid has high nucleation rate in water. Then further, using classical nucleation theory, the software determines the nucleation parameters by curve fitting this equation, and which are plotted here. And from these graphs, the intercept and the slope will give us the parameters. This A, which is kinetic parameters, which represents the number of active sites available for nucleation. And from the slope, we determine the B, which is thermodynamic parameter, and which represents the activation energy required for nucleation to happen. And if we see the effect of solvent systems, we can see that the kinetic parameter decreases with increase in alcohol concentration, whereas thermodynamic parameters increases with increase in alcohol concentration, which indicates that more activation energy is required to start nucleation in alcohol binary solvent systems. These are the images taken during pooling crystallization experiments, again in different solvent systems. Here we can see that in water, more cubic shaped crystals were formed, and with increase in alcohol concentration, more elongated crystals were formed, resulting in rod shaped crystals in methanol and ethanol. And similarly for water isopropanol solvent system, initially in water, more cubic shaped crystals were formed with increase in alcohol or isopropanol solvent system. More elongated crystals were formed, and in pure isopropanol, cluster of needle-shaped crystals were formed. And the reason for this is attributed to the change in the growth rate mechanism. With the addition of alcohols, it decreases the mass transfer and increases the surface integration, which results in growth in one crystallographic axis. And from these images, we can see the change in the crystal habit, but to analyze or characterize in terms of particle shape and particle size, the new crystalline V2, it takes the help of the AI. So AI is advanced technology which has the ability to detect particles that it has seen before. The instrument, it gathers a set of images where particles are clearly marked, and these set of labeled images form the basis for teaching AI to detect particles in new pictures. So how it works, first the input. The process begins with providing an input with an image containing the particles. Then the AI system uses the neural network, which from the deep learning technology to detect particles in the new image. It looks for specific features and characteristics which indicate the presence of the particles. Then the particle separation, it differentiates in different characteristics in terms of size and shape. And then it gives an output which indicates the particles with size and shape characteristics. The shapes, it can be characterized in different forms like non-convex, quasi-equivalent, which is like equal in all direction, and it represents mostly cubic shape, then needle, platelets, and spheres. Then different particle parameters are particle size, which is equivalent sphere diameter, contour parameter, contour area, ellipse shape factor, convex hull parameter, and convex hull area. Further, the instruments determines the particle size distribution and parameters in terms of D10, D50, and D90. So this is comparison of or validation of glass weights of 100 micron size. So the AI uses the latest technology, which is able to detect the individual crystals pixel-wise. So the conclusion is a state-of-the-art particle detection, which can detect individual particles separately. I would like to end this talk by looking into collaboration with CMAC. And in last 2 days, you have seen these during the lab tour and so many presentations. And this is crystalline with the robotic arm. Here you can automatically program the experiments, and the robotic arm can put the vials in the crystalline, and you can work overnight, and it will quickly accelerate to the translation to industries. I would like to thank CMAC for giving me this opportunity, and we'll look forward more to collaboration with CMAC, and I'm happy to answer any questions. Thank you.
Hi, thanks. Good presentation, and it's nice to see Technobis upping their game and the rate of things happening. Question for you though is, so for the nucleation rate data, you showed, I don't know, there were maybe 6 or 8 panes on there, and each one had 4 or 5 different conditions, and then each one of those had 100 experiments sort of associated with it. So on that page, there's like 3,000 experiments. I'm
Yes.
wondering how long that takes.
For this, in the new Crystal 16 instrument, you can program your experiments and you can run. Ideally, you need to do 80 experiments at 1 supersaturation. You can program your experiments in the Crystal 16 and you can leave it for weeks. So you don't have to do anything. And it will automatically do the calculations. These plots are plotted by the software, not by me. So you have to maybe few weeks, and if you run in multiple, because you can run in multiple at the same supersaturation, you can do multiple runs, and then I think for one solvent you can do in week or 2 weeks. So yeah. Thank you. Thank you.
Thank you very much.
Thank you.
Thank you very much.